Danilov, who's going to tell us about FESOM applications to large-scale ocean modeling.
Hello to everybody, and I hope that this talk will be kind of leisure talks compared to talks that we have heard in the morning, because I will be mostly telling you what we are practically doing and less about mathematics, and in case of questions on mathematics I would like to answer just separately because it will take a lot of time. The basic idea, you see, of all this effort is that we are interested in simulating large-scale ocean, and we are in principle willing to have a possibility of nesting or of increased resolution where we just need it. And in the ocean case, it is frequently places like this place or Labrador Sea or this place or places like this, in order to simulate flows through the passages or in order to resolve dynamics that would be otherwise too damped, right? And for this purpose, what is FESOM? FESOM is full primitive equation hydrostatic model that is coded with finite element method, and as our discretization, we are using triangular mesh, which is just arbitrary triangular mesh. Then everything is split into prism, and we have several versions of code, and most frequently used one is based on the fact that every prism is also split into 3 tetrahedra. The point is that we are using linear functions to represent our fields, and in the tetrahedral case, it's just linear on tetrahedron, and which gives you a possibility to just take arbitrary layering in your ocean without doing any changes to the code. Everything is automatically taken into account. This has also drawbacks because computational stencil in 3D, if you are taking particular nodes and picking up all tetrahedrons that are sitting in its computational stencil, is a little bit horrible, and this introduces, if you are looking into detail, some computational noise into tracer fields. But this is well controlled, and it's easy to deal with. We are working on several other codes which exist, and I just experimented with them, and they are much promising because they are much faster than finite element discretization. But as major motivation is that P1, since it's kind of A grid or collocated grid discretization, it still needs stabilization against pressure modes. So it's stabilized code, and stabilization introduces some biases into certain balances, like it's very difficult, for example, to keep true energy balance with stabilized code. It's very easy to keep mass conservation, tracer conservation, and for that reason we are looking at different variants. So vertex, finite volume setup, last PDE, Schmerz and Smolarkevich were presenting this. I tried it. It still has pressure modes, and it's, well, just faster than P1, but otherwise it is not worse. And what we are currently trying is a cell vertex setup that is very close to the ZM mesh on hexagonal meshes. And well, this is something that we are doing, and as I said, I would like to answer all possible questions just separately and outside of this. So the concept that, as we are understanding it here, is perhaps illustrated by this meshing. We are using coarse global meshes for entire ocean, but then we are zooming in the area of interest. And zooming implies that you have quite strong stretching or refinement factor, which is very typically like 30 or 50, right? So from 100 kilometer to something like 5 or 3 kilometer, sometimes to half a kilometer. And this is a case where we were doing simulation of East Greenland current. It's coastal current that is attached to the coast of Greenland. So it's here, and this is so this is interpolation on regular mesh which gives you an idea of velocity field, how it flows, and you see that there are many details and you really need resolution here. So I will continue further and will just tell about several practical examples of what we are doing, and this is work by Claudia Weckerle, and the point here is freshwater transport through Canadian archipelago, and in order to have it properly we are really increasing the resolution here to something that is not visible on this mesh. And the point is that transport of fresh water through the passages, so there are two main, this one and this one, depends really on resolution. We are doing comparison of two meshes, so one is quarter resolution, quarter degree here, and the other one is just 5 kilometer here, and we are looking at fresh water transport through the major straits. And while in the case of Lancaster Sound, you see that quarter degree would be sufficient, this one requires really high resolution. And we also doing comparison with observations, and the blue one is much closer to what really is found. Another case which I will show you is a simulation of Weddell Sea polynya. So this shows you just fragment of mesh in Weddell Sea, which goes to 3 kilometers at 60 kilometers, and it goes to like 100 global ocean. And what is specific, so the color here is just topography, and what is specific here, you see the following. So it's all covered with ice, and during wind event there are polynya forming. So this is sea ice concentration that shown. You see this bluish spot here is spot where ice is drifting offshore and water is exposed to cold air. Correspondingly, it refreezes, and when it freezes, of course, there is a lot of brine rejection, and you see here surface bottom salinity events that are forming, and you see that this salinity tongue goes all the way down, and it determines what you see, so the fate of bottom water produced here. So you really need to see this, to have these polynyas properly resolved in order to keep proper properties of waters, and this is possible to do with such type of modeling. This gives you just comparison of simulated ice concentration with satellite observations, and you see that model performs quite nicely with just standard and SEP reinforcing. It gives you a lot of say hope that including such events will be vital for say future climate modeling, and it's possible with this variable grid resolution. Another case that I will be say willing to show you is something that Ralph Timmerman from our institute is involved. It is ice shelf modeling. This shows you just a piece of Weddell Sea in say bad projection, but so the colored part is in reality part where you have ice shelf, so it's covered with ice, and water can come underneath this ice. And what happens that in reality the freezing temperature is a function of pressure, and so water that touches ice here is too warm, so it's 2 degree water, but it's too warm, and it melts this ice, so there is a lot of fresh water release, so it gets more buoyant and goes up, and you're getting such type of pump which has two implications. It leads to melting of ice sheet, so sea level rise, and it also changes the water masses quite considerably, which it has also implication on bottom water formation, right? And this illustrates what we are doing. So that's just possible in our model without any problems. We are doing such type of layering, and of course it requires a little bit of work that this place is not breaking down, because a lot of instabilities may occur at that particular place. But it's vital to have such type of structure, because you have to keep proper water masses across these layers, because in this particular case your isothermals are more or less following topography. This study has a lot of say implications, and well, I'm sorry for this because it's some drawback of visualization. So here we are giving a comparison of estimate of basalt melting rate for major glaciers or major ice sheets that are existing in the Southern Ocean. So this is this one, and you can find the other. So there are two different models. This one is estimate made with FESOM. This is estimate made with model called BRIOS, and green is estimate made by observationalists. And you see that estimates that we are doing are quite, in many cases, quite good, for at least for the major ice sheets, and they are getting offset for smaller one. Here is a story which is happening. So it's kind of a future climate projection that we are integrating this for certain amount of years, given post-forcing. And what you see is the fact that with time more and more water is entering underneath the ice shelf and produces excessive melting. So melting rate is considerably increasing, and there is quite a lot of implications due to this. So that's finite result, and so I will perhaps skip this. This is another set of simulations we are doing. It concerns Arctic Ocean, and here what we are comparing is global ocean, and focus is on Arctic Ocean. Here it's 24 kilometer, and here it's 9 kilometer resolution in Arctic, and the depth is 300 meters. It shows you difficulties or problems that we have to work with. It's the fate of Atlantic water, which is here, warm water. So it should go like this here, and it should continue all the way along the coast. And obviously we have some problem at that particular place, because especially in the case of high resolution, because a lot of water is just deflected and stays in this basin instead of continuing all the way here. But that's a problem we are working at, and it involves a lot of features, and in particular it involves to strong extent dynamics in this region and dynamics of water masses that goes through the Barents Sea. So the resolution will be then again necessary to learn what is going on. We did a lot of different type of tests, which are not, say, the simple tests as we have typically here in this community. These are tests mostly intercomparison with other models. So we did type of intercomparison of FESOM under core 1 forcing. So this is 500 years of simulation under climate perpetual year forcing, and this shows mesh that we were using, sea surface height. So many other models were involved, including those listed here. And so in many respects we see that circulations that we are getting and all parameters that we are getting are quite comparable to what other people have. And this illustrates you the scatter that you see in AMOC stays for Atlantic Meridional Waternian Oscillation, and you see that even given same atmospheric forcing, right, different models behave themselves quite differently and scatter as time progresses. And this tells you the major difficulty in all the modeling first issue. Second issue that you see that there is at least 50 years time scale of adaptation that every model follows, and this is approximately the time scale it takes fast Brooklyn Crosby wave to cross basins like Pacific or Southern Ocean. We are doing also, or we are taking part currently in Core 2 intercomparison project that is carried in the framework of Cliver initiative, and it assumes 5 periods of standard and SEP or Core 2 forcing that is 60 years long. So it's shown here, and this shows you the observed mean trend of temperature and say typical heat flux. So you see that over these 5 periods there is still no equilibration in ocean model, and this is linked to the fact that forcing is somehow biased always toward the toward your model, and this shows variability, so surface heat flux, which shows you that after the first cycle everything is converging and variability is nicely represented, and this is residual surface heat flux, and you should see that there is convergence, so it's necessary, which is also seen here, but it's necessary to wait much longer for that. We checked that you see all obvious indices nicely modeled, but this sits mostly on the fact that atmospheric forcing is appropriate, and same is concerning to the Pacific Decadal Oscillation Index. So model reproduces this, but this is not surprising because it sits in. Finally, I would like to say that we have currently coupled system where FESOM works together with ECAM6 model, and we are doing a lot of different tests now to see where we are. So it's one example with meridional overturning. So we see that sometimes we are getting regions with much larger overturning in coupled system, and we are looking at, as I said, different indices. This is work that is done by Tito Sembler from our institute, and in some respects we are okay. In some respects we still need to look into our bulk formulas and parameterizations. Well, same here. So it's again a linear index, which looks quite nice if we compare to what is observed. I mean, same period, same amplitude, and in reality, I'm close to conclude. What I tried to show you is that the concept of regional focus works pretty well, despite the fact that say mathematically we are really doing quite a lot of stretching, so there is this interfacial zone where our dynamics cannot be accurate. But the point is that as a rule also our dissipation is tuned, and so we never see a lot of danger from these regions. On the contrary, we see that the memory is forgotten quite fast, and there is not we don't see obvious artifacts of this, right? There is more difficult question, which is whether resolved dynamics, like the production of deep waters is that are appropriate, will be, say, maintained by core scale of the model, right? Because there will be more mixing perhaps, and so on. So it's not, this part is not really obvious and may require a lot of special efforts, right? And we are currently running, say, several projects, and this is something that we are going to start, or almost started with DOT together, and this is planned when I will be back. And it is used by many people right now in our institute, and there are many hopes that coupled system will be always very, very convenient to study again impact of regional scale processes in the ocean on global ocean atmosphere circulation. Thank you very much.
We have time for questions.
Have you investigated what the effect is of how rapidly you refine the mesh in the various regions in the ocean?
Well, I looked into many examples, just playing with baroclinic instability in the channel. And on those simple examples, you of course see kind of retardation. So if there is zonal flow, right? So you have coarse scale, then you refine, then there is fine scale. Of course, there is zone of retard where there is no baroclinic instability because there are no perturbation in the flow coming from upstream, from downstream side.
But in your in your realistic situations, have you tried changing that parameter and seeing
in realistic situation? It's very difficult to say, right? Because there is no obvious measures to compare this, right? What we can judge only is that you don't have kind of spurious activity like eddies penetrating the coarse part and somehow degrading. This never happens because, as I said, diffusivity and viscosity are scaled properly, right? But I would say the question rather remains on the level, we have produced proper water masses, so we resolve this, say, downslope processes. So we are getting pool of water, but then what happens to this water, right? Then, of course, it will be more diffused if your mesh is coarse, right? There is no miracles in that, right? And the question is whether it's okay. Perhaps not. Yes, these issues we have not looked into, but this can be of importance, right?
Sergey, when you couple with the Echam model, did you ever try, or do you have experience? That's basically my question. Do you have experience what happens when you have, for example, a highly non-uniform grid in the ocean and a relatively uniform grid in the atmosphere?
That's, in reality, is a tough question which we are working currently, because certainly what happens that there is disparity between resolution and between variability. Say that the ocean model has a fine mesh and atmosphere has a relatively coarse mesh. And so what we are thinking about currently are kind of stochastic parameterizations that will be used to regenerate variance on small scale, and on the contrary to take into account information that is averaged to the atmosphere somehow, right? So this is something that is still an issue, yeah, because of course there is damping from the fact that atmospheric dynamics is so coarse for ocean parts.
Thank you very much.